Somewhere in the vast darkness between stars, a single photon travels in perfect silence. It has no mass, no resistance, no friction to slow it down. It moves at the fastest speed the universe permits, a velocity so fundamental that it shapes the very fabric of reality. For this photon, time does not pass. Distance does not exist in the way we understand it. From the moment it leaves a distant star to the moment it strikes your eye, the photon experiences no duration at all. Its journey of millions of years, as we measure it, happens in an instant from its own perspective. And this strange fact, this peculiar relationship between speed and time, hints at something extraordinary about what would happen if a human being could somehow approach that same cosmic velocity. We live our lives at speeds so slow, relative to light, that we never notice the subtle ways the universe bends around motion. A car on a highway, a jet crossing an ocean, even a rocket leaving Earth's atmosphere. All of these move at velocities so modest that the strange effects predicted by physics remain invisible to us. But hidden beneath our everyday experience lies a deeper truth, one that only reveals itself as velocities climb toward that ultimate limit. The faster you move through space, the slower you move through time. The closer you approach the speed of light, the more dramatically the universe transforms around you. And if you could somehow reach velocities truly close to that cosmic maximum, you would enter a realm where time, space, distance, and even your own experience of reality would become almost unrecognizable. What would this actually mean for a human being? How would it feel to travel at 90% of the speed of light, or 99%, or even closer? What would you see? What would happen to your body? How would your relationship with the universe itself fundamentally change? These questions lead us into one of the most remarkable territories in all of physics, a place where our intuitions fail completely, but where the mathematics reveals truths stranger and more beautiful than anything we might have imagined. To begin understanding this journey, we need to appreciate why the speed of light holds such a special place in physics. It is not merely the speed at which light happens to travel. It is woven into the structure of space-time itself, appearing in equations that govern everything from electricity to gravity to the behavior of subatomic particles. When Albert Einstein developed his special theory of relativity in 1905, he built it upon two deceptively simple principles. First, the laws of physics are the same for all observers, moving at constant velocities relative to one another. Second, the speed of light in a vacuum is the same for all such observers, regardless of how fast they themselves are moving. From these two principles, everything else follows. Time dilation, length contraction, the equivalence of mass and energy, and the impossibility of exceeding that cosmic speed limit. The constancy of light speed seems almost paradoxical at first. If you are standing still and shine a flashlight, the light travels away from you at approximately 299,792 kilometers per second. Now imagine you are on a spacecraft moving at half the speed of light, and you shine that same flashlight forward. You might expect the light to travel at 1.5 times the speed of light relative to a stationary observer, your speed plus the light's speed. But it does not. The stationary observer still measures the light moving at exactly 299,792 kilometers per second, not faster. This seems impossible according to our everyday understanding of motion. Yet countless experiments have confirmed it with extraordinary precision. How can this be? The answer lies in what must change to make this constancy possible. If the speed of light cannot change, then time and space themselves must adjust to accommodate it, and they do. When you move at high velocity, your clocks tick more slowly compared to those of a stationary observer. Distances in your direction of motion contract. These are not illusions or measurement errors. They are real, physical changes in how space-time behaves for moving objects. And the faster you move, the more pronounced these effects become. At ordinary speeds, these relativistic effects are so minuscule that they escape detection without extremely sensitive instruments. A passenger on a commercial airplane experiences time passing ever so slightly slower than someone on the ground, but the difference amounts to mere nanoseconds over an entire flight, meaningless in practical terms. But as we contemplate velocities approaching significant fractions of light speed, the effects transform from negligible curiosities into dominant features of physical reality. Consider what happens at 10% of the speed of light, roughly 30,000 kilometers per second. This is already far faster than any human has ever traveled, far faster than any spacecraft we have built. The Voyager probes, among the fastest objects humanity has ever launched, travel at about 17 kilometers per second. 10% of light speed is nearly 2,000 times faster than that. At this velocity, time dilation becomes measurable, but still modest. A clock on the spacecraft would tick about 0.5% slower than a clock back on Earth. Over a journey of many years, this would accumulate into hours, perhaps days of difference. Noticeable to precise instruments, but not dramatically life-altering for the travelers. But what if we push higher? At 50% of the speed of light, time dilation grows more significant. Now the moving clock ticks at about 87% of the rate of the stationary clock. For every hour that passes on Earth, only about 52 minutes pass for the traveler. A one-year journey from Earth's perspective would feel like about 10.5 months to the person making the trip. The difference is becoming meaningful, something a human would actually experience as a discrepancy in aging between themselves and those they left behind. And this leads us to something even more surprising. At 90% of the speed of light, the effects become dramatic. Time for the traveler passes at only 44% of the rate it passes for a stationary observer. For every year that ticks by on Earth, the traveler experiences only about 5.5 months. If you departed Earth and traveled for what felt like 1 year to you, nearly 2.5 years would have passed back home. People you left behind would have aged more than twice as much as you. Events would have unfolded, seasons changed, lives lived, all while you experienced a much shorter span of personal time. Push even closer to light speed, and the transformation becomes more extreme still. At 99% of light speed, time dilation reaches a factor of about 7. 1 year of traveler time corresponds to 7 years back on Earth. At 99.9%, the factor increases to about 22. At 99.99%, it climbs to 70. A journey that feels like a single year to the traveler would see 70 years elapse for everyone else in the universe. Entire generations could be born, live their lives, and pass away while you experience what feels like a modest interval. What would this mean for a human traveling through space at such velocities? The psychological implications alone are staggering. You would depart knowing that your return if it ever came, would find a transformed world. Friends and family would have aged decades in your absence. Children would have grown old. Societies would have evolved. History would have marched forward without you, and your memories of the world you left would become artifacts of a distant past. The traveler at near light speed is, in a very real sense, a time traveler, not into the past, but into the future, skipping over the intervening years that everyone else must live through moment by moment. But before we continue exploring the human experience of such journeys, we need to understand what makes these velocities so difficult to achieve in the first place. The challenge is not merely engineering more powerful engines or finding better fuels. The challenge is fundamental, built into the laws of physics themselves, and it relates to the nature of energy and mass at relativistic speeds. In everyday physics, the energy required to accelerate an object depends on its mass and the velocity change you wish to achieve. Double the mass, and you need double the energy. Double the velocity change, and you need 4 times the energy, because kinetic energy scales with the square of velocity. These relationships hold reasonably well at ordinary speeds. But as velocities approach light speed, something changes. The effective inertia of an object, its resistance to acceleration, begins to increase. Not because more matter is being added, but because the relationship between energy and velocity transforms in the relativistic domain. At low speeds, adding a fixed amount of energy produces a predictable increase in velocity. But as you approach light speed, the same amount of energy produces less and less additional velocity. It is as though the universe itself is pushing back against your acceleration, demanding ever more energy for ever smaller gains. At 90% of light speed, an object's effective inertia has already more than doubled compared to its rest state. At 99%, it has increased by a factor of 7. At 99.9%, by a factor of 22. The closer you get to light speed, the more energy you need to get even closer. And this relationship diverges toward infinity as you approach the limit. This is why nothing with mass can ever actually reach the speed of light. It would require infinite energy, which is a physical impossibility. The speed of light is not a barrier that sufficiently powerful technology could break through. It is a fundamental asymptote, a limit that can be approached ever more closely, but never reached or crossed. This is built into the structure of space-time itself, a consequence of how energy, mass, and velocity relate in Einstein's universe. So how close could we truly come to light speed? In principle, there is no lower limit to how small the remaining gap can be. You could reach 99% or 99.9%, or add as many 9s as you like. Each additional 9 requires vastly more energy than the last, but none represents a hard boundary. The practical limits are set by the energy available and the engineering challenges of harnessing and directing that energy. For any realistic propulsion technology we can currently envision, even reaching a few percent of light speed represents an almost insurmountable challenge. But the laws of physics do not forbid velocities much closer to the limit. They merely make such velocities extraordinarily expensive in terms of energy. And this raises another quiet question. If a spacecraft somehow achieved a velocity very close to light speed, how would the universe appear to its passengers? What would they actually see when they looked out the windows? The answer involves some of the most counterintuitive visual effects in all of physics, phenomena that transform the appearance of the cosmos in ways that seem almost hallucinatory. Light itself behaves strangely when you are moving at relativistic velocities. One effect, known as aberration, causes the apparent positions of stars to shift toward the direction you are traveling. At low speeds, this shift is negligible. But at high relativistic velocities, stars that would normally appear off to your sides seem to crowd toward the front of your spacecraft. The faster you go, the more extreme this crowding becomes. At very high fractions of light speed, nearly the entire sky would appear to concentrate into a brilliant disk ahead of you, with only a dark void behind. Accompanying this distortion is a profound change in the colors of light. Stars ahead of you appear blue-shifted, their light compressed to higher frequencies as you rush toward them. Stars behind you, if any remain visible, appear red-shifted, their light stretched to lower frequencies as you race away. At sufficiently high velocities, the blue shifting becomes so extreme that visible light from stars ahead transforms into ultraviolet radiation, then X-rays, then gamma rays, frequencies invisible to human eyes and potentially dangerous to human tissue. The red shifting behind would push visible light into infrared, then microwaves, then radio waves, effectively rendering the trailing universe dark and invisible. What would a human traveler actually perceive? Without technological aids, the view would be deeply alien. A blazing concentration of light ahead, shifted beyond the visible spectrum into harmful radiation. A dark emptiness behind. The familiar constellations distorted beyond recognition, squeezed together into unfamiliar patterns. The universe itself would appear to have transformed, not because it actually changed, but because your motion through it altered how its light reaches your eyes. But this is only the beginning of the strangeness. To make sense of relativistic travel, we must step back for a moment and consider another phenomenon that shapes the traveler's experience: length contraction. Just as time dilates for a moving observer, distances contract in the direction of motion. The faster you travel, the shorter the distances ahead of and behind you appear to become. This is not an optical illusion, but a genuine feature of relativistic space-time, as real and physical as time dilation. At 90% of light speed, lengths in your direction of travel contract to about 44% of their rest length. A distance that measures 1 light year to a stationary observer would measure only about 0.44 light years to you. At 99% of light speed, this contraction increases to about 14%. At 99.9%, to about 4.5%. The universe ahead of you, in a very real sense, shrinks. What does this mean for interstellar travel? Consider a journey to a star system 10 light-years away. At conventional speeds, this would take tens of thousands of years. Even at 10% of light speed, still fantastically beyond our current capabilities, the journey would take a century. But at 90% of light speed, something interesting happens. From Earth's perspective, the journey takes slightly over 11 years. The spacecraft cannot exceed light speed, so it must take longer than 10 years to cover 10 light years. But from the traveler's perspective, both time dilation and length contraction combine to create a very different experience. The traveler experiences only about 5 years of subjective time, and the contracted distance ahead means they are covering what appears to them as only about 4.5 light years. Push the velocity higher, and these effects compound. At 99% of light speed, the Earth frame journey time is just over 10 years, but the traveler experiences only about 18 months. At 99.9%, the traveler's experience shrinks to about 5 months. The 10 light-year journey, which would require 10 years, even for a beam of light, feels to the traveler like a much shorter trip because both their clock and their measuring rod have transformed. This leads to a remarkable possibility that has fascinated physicists for over a century. In principle, given sufficient velocity, a human being could traverse enormous cosmic distances within a single lifetime. The distances do not actually shrink in any absolute sense. The universe remains as vast as ever for observers at rest. But for the moving traveler, personal time passes so slowly, and lengths contract so dramatically that journeys across the galaxy become theoretically survivable. A trip to the center of the Milky Way, roughly 26,000 light-years distant, would take at least 26,000 years from Earth's perspective. But a traveler moving at 99.99% of light speed would experience only about 370 years, still far longer than a human life, but far shorter than the millennia ticking by back home. At even higher velocities, with enough additional nines after the decimal point, even this journey could be compressed into decades of subjective time. The universe, in this sense, is accessible to a sufficiently fast traveler in ways that seem impossible from our stationary perspective. The practical barriers are immense: the energy requirements, the engineering challenges, the hazards of the journey. But the laws of physics do not forbid such exploration. They merely make it extraordinarily difficult. And this brings us to the hazards themselves. The physical dangers that would confront any spacecraft attempting to travel at relativistic velocities. The space between stars is not perfectly empty. It contains a thin scattering of atoms, primarily hydrogen, along with dust grains, cosmic rays, and other particles. At ordinary speeds, this interstellar medium is essentially harmless, far too sparse to affect a passing spacecraft in any meaningful way. But at relativistic velocities, everything changes. The energy of a collision depends on the relative velocity between the colliding objects. A hydrogen atom drifting peacefully through interstellar space becomes a deadly projectile when you slam into it at 90% of light speed. The kinetic energy of even a single proton at such velocities becomes comparable to that of a fast-moving bullet in conventional terms. And a spacecraft traveling through space would encounter billions of such particles per second, each one delivering its tiny but significant impact. The cumulative effect is troubling. At high relativistic velocities, the interstellar medium becomes a continuous bombardment, a stream of radiation and particle impacts that would erode surfaces, damage equipment, and potentially harm biological passengers. Shielding might help, but even shielding has limits. When a high-energy particle strikes a physical barrier, it does not simply stop. It produces secondary particles, showers of radiation that can penetrate deeper into the structure. The shield itself becomes a source of dangerous radiation. At the most extreme velocities, even individual atoms of hydrogen carry energies comparable to cosmic rays, the most energetic particles known to physics. These would produce cascades of secondary radiation with each impact, exposing the interior of the spacecraft to continuous irradiation. How would this affect human passengers? The biological damage would accumulate over time, increasing cancer risks, damaging DNA, potentially causing acute radiation sickness if the flux became high enough. And atoms are not the only concern. The interstellar medium also contains dust grains, tiny particles of silicate, and carbon compounds scattered by ancient stellar winds and supernova explosions. These grains are small, typically only a micrometer or so across, but at relativistic velocities, a collision with even a microscopic dust grain would release enormous energy. A speck of dust weighing a millionth of a gram, striking a spacecraft at 99% of light speed, would deliver energy equivalent to several kilograms of explosive. At higher velocities, the energy scales upward with the square of the velocity, quickly reaching truly destructive levels. How could a spacecraft survive such impacts? The challenge is immense. Active deflection systems, using electromagnetic fields to push charged particles aside before they strike, might help with some hazards, but would do nothing against neutral atoms or dust grains. Ablative shielding, designed to vaporize and carry away the energy of impacts, might protect against occasional dust collisions, but would steadily erode over the course of a long journey. The interstellar medium, so sparse and insignificant at ordinary speeds, becomes a formidable obstacle at relativistic velocities. But this raises another quiet question, one that probes even deeper into the nature of the journey. Suppose these engineering challenges could somehow be solved. Suppose a spacecraft could be built that survives the radiation, the particle bombardment, the dust impacts. Suppose it could accelerate to 99% of light speed and maintain that velocity across the light years. What would the journey actually feel like for the human passengers inside? Here, we must consider the acceleration phase itself. A spacecraft cannot simply leap to relativistic velocity instantaneously. It must accelerate, and that acceleration takes time and produces physical effects on everything aboard. The human body can tolerate only limited acceleration before discomfort sets in, and only slightly higher acceleration before injury or death results. Fighter pilots experience brief moments of high acceleration and must wear special suits to prevent blackouts. Astronauts during launch experience several Gs, several times Earth's surface gravity, for minutes at a time. For a journey at relativistic velocities, the acceleration phase could dominate the travel time if performed gently, or could compress into a brutal interval if performed quickly. A sustained acceleration of 1 g, equal to Earth's surface gravity, would feel comfortable to passengers, mimicking normal gravity and allowing them to walk, eat, and sleep in familiar ways. At this rate, how long would it take to reach 90% of light speed? Calculating this requires care, because relativistic effects begin to matter as velocity increases. At 1 g of constant acceleration, reaching 90% of light speed would take approximately 2 years of ship time. 99% would require about 5 years. 99.9%, roughly 7 years. These are substantial periods, but not beyond human endurance. The passengers would experience years of steady acceleration, living in conditions that feel much like standing on Earth's surface, before finally reaching their cruising velocity. But those years of ship time correspond to much longer periods in the external universe. The acceleration phase itself involves increasing velocities, which means time dilation is continuously changing throughout the process. By the time the spacecraft reaches its cruising speed, years or even decades may have passed on Earth. even if the passengers have experienced only months or a few years. The journey becomes a one-way trip into the future from the moment acceleration begins, long before cruising velocity is achieved. And this leads us to something even more surprising about the nature of such journeys. The energy required for acceleration must come from somewhere, must be carried aboard the spacecraft or delivered from external sources. If carried aboard, the fuel mass becomes part of the problem. The more fuel you carry, the more mass you must accelerate, which requires more fuel, which adds more mass. This circular dilemma, known as the tyranny of the rocket equation, limits how much velocity change a self-contained spacecraft can achieve. For chemical rockets, this limit is severe. The exhaust velocities of chemical reactions are only a few kilometers per second, far too slow to efficiently accelerate a spacecraft to relativistic speeds. Even nuclear propulsion, with its much higher exhaust velocities, struggles to bridge the gap. The most efficient theoretical propulsion systems, antimatter rockets for example, offer exhaust velocities approaching light speed. But even these face fundamental limits when trying to achieve relativistic cruising velocities. One approach that physicists have considered is the external propulsion concept, where the spacecraft does not carry its fuel, but instead receives energy from an outside source. A powerful laser array on Earth, or in the solar system, could beam concentrated light toward a spacecraft equipped with a large reflective sail. The pressure of the light, though gentle, would continuously accelerate the sail and its payload, potentially reaching relativistic velocities over time. The advantage is that the heavy power source stays behind, and only the payload must accelerate. The disadvantage is that the beam must remain focused on an increasingly distant, increasingly fast-moving target, a technical challenge of staggering proportions. Another concept, more speculative still, involves harvesting material from the interstellar medium itself. Using the hydrogen atoms that would otherwise be hazards is fuel for a fusion reactor. A ramjet design might scoop up these atoms with an enormous magnetic funnel, fuse them for energy, and expel the products for thrust. In principle, such a design could accelerate indefinitely without carrying fuel, limited only by the density of the interstellar medium and the efficiency of the fusion process. In practice, the technical challenges appear overwhelming, and the physics suggests that the drag from collecting the fuel may exceed the thrust from burning it at most realistic velocities. To make sense of these challenges, we must acknowledge that reaching truly relativistic velocities remains beyond current human capability by enormous margins. The fastest spacecraft ever launched, the Parker Solar Probe, achieves speeds of about 200 kilometers per second near its closest approach to the Sun. This is less than 0.1% of the speed of light. The gap between our present abilities and relativistic travel is not one of degree, but of kind, requiring advances in physics and engineering that we cannot yet clearly foresee. Yet the laws of physics do not forbid such travel. They make it difficult, expensive, dangerous, but not impossible. And this distinction matters because it means that the strange effects of relativistic motion are not merely theoretical curiosities. They are features of a realm that our descendants might someday actually experience. What happens to time when we approach such velocities? This question, which we have touched upon already, deserves deeper exploration. Time dilation is not merely a slowing of clocks in some mechanical sense. It is a slowing of all physical processes, chemical reactions, biological metabolism, thought itself. To a traveler, at 99% of light speed, the universe does not appear to be running fast. From their perspective, everything aboard the spacecraft proceeds normally. A heartbeat takes the usual fraction of a second. A thought unfolds at the usual pace. A meal digests in the usual hours. The slowing is apparent only in comparison with the external universe, which seems to be racing ahead at 7 times the normal rate. This creates a profound asymmetry in experience. The traveler lives through what feels like a normal span of time, perhaps years, perhaps decades, depending on the journey. But during that personal interval, far more time passes for everyone and everything else. The traveler returns to a future they never lived through, emerging into a world that is aged without them. Physicists sometimes call this the twin paradox, though it is not truly a paradox. If one twin stays on Earth, while the other makes a relativistic journey to a distant star and back, the traveling twin returns younger than the one who stayed home. This seems symmetrical at first glance. Couldn't the traveling twin claim that it was Earth that moved away and returned? But the symmetry is broken by the fact that the traveling twin must accelerate to depart, decelerate to turn around, and accelerate again to return. These accelerations distinguish the two twins' experiences and break the apparent symmetry. The traveler really does age less. The mathematics is unambiguous, and experiments with atomic clocks have confirmed the effect in microcosm. How would this affect the psychology of such travelers? We have no experience to draw upon, no historical examples of humans skipping decades into the future. The closest analogies, long sea voyages in earlier centuries perhaps, where sailors returned to find homes and families transformed, only hint at the magnitude of the dislocation. A relativistic traveler might return to find that everyone they knew has died, that languages have evolved, that societies have restructured themselves, that the very culture they remember exists only in historical archives. The traveler would be a living artifact, a person from the past appearing in a future they cannot fully comprehend. And this brings us to communication, another aspect of relativistic travel that deserves careful attention. Even if a spacecraft could maintain contact with Earth throughout its journey, the time delays would be severe. At the moment of departure, a message sent home would arrive promptly. But as the spacecraft accelerated toward relativistic velocities, Doppler effects would stretch the signals, lowering their frequency and spreading out the information they carried. From Earth's perspective, the spacecraft's transmissions would become increasingly slow and low-pitched, like a recording played at decreasing speed. Eventually, near cruising velocity, each message would arrive drastically time-dilated, taking hours or days to deliver what was spoken in minutes. The return messages would suffer the inverse effect. Signals sent from Earth, which experiences time at the normal rate, would reach the spacecraft blue-shifted and compressed, arriving in a rapid barrage that might need to be slowed down for comprehension. The conversation would become asynchronous in a profound way, with years of Earth time corresponding to months of ship time, making real-time dialogue impossible and even exchanges of messages feeling increasingly disconnected. Over the course of a long relativistic journey, this communication lag would become unbridgeable. A traveler journeying to a star 10 light-years away could send a message upon arrival that would not reach Earth for 10 years. A response would take another 10 years to return. By the time an answer arrived, 20 years would have passed on Earth, but perhaps only a few years for the traveler. The traveler would be conversing with people who had aged decades between messages, who might have changed careers, retired, or died in the intervening time. The isolation of relativistic travel is not merely physical but temporal, a separation in time as profound as the separation in space. But before we continue exploring the human dimensions of such journeys, we need to understand one more physical phenomenon that would shape the traveler's experience: the distortion of mass and momentum in the relativistic domain. We touched earlier on the increasing resistance to acceleration that objects experience as they approach light speed. This effect is sometimes described in terms of relativistic mass, a concept that has fallen somewhat out of favor among physicists, but that captures something real about how moving objects behave. At relativistic velocities, an object carries momentum far greater than its rest mass, and velocity alone would suggest. A spacecraft traveling at 90% of light speed carries momentum as though it had more than twice its rest mass. At 99%, the factor is 7. At 99.9%, 22. This increased momentum has practical consequences. Steering becomes more difficult because the force is required to change direction scale with momentum. Collisions become more catastrophic because the energy released scales with momentum. The spacecraft, though unchanged in its physical composition, behaves as though it has become much heavier. This relativistic momentum also relates to energy in a profound way. Einstein's famous equation, E equals mc squared, describes the energy equivalent of rest mass. But a moving object carries additional energy in its motion, and at relativistic velocities, this kinetic energy becomes comparable to or greater than the rest mass energy itself. A spacecraft traveling at 99% of light speed carries kinetic energy roughly equal to 6 times its rest mass energy. This is an almost inconceivable amount of energy, far exceeding anything humanity has ever harnessed for propulsion. What would such energy mean in practical terms? Consider a modest spacecraft with a rest mass of 100,000 kilograms, roughly the size of the International Space Station. At 99% of light speed, its kinetic energy would be equivalent to about 500 million billion joules. This is roughly equal to the total annual energy consumption of a medium-sized country. Achieving such velocities would require generating and applying this much energy to the spacecraft. And bringing the spacecraft back to rest would require absorbing it again. The engineering challenges are almost unimaginable. And yet, as we noted earlier, there is no fundamental law prohibiting such energies from being generated and applied. They are merely enormous, not infinite. The gap between humanity's current capabilities and relativistic travel is vast, but it is a gap of scale, not of principle. How would physics reshape our understanding of identity and motion? This philosophical dimension of relativistic travel often goes unexplored, but it raises questions that touch on the nature of personal continuity and the meaning of existence across time. A traveler who ages 5 years while Earth ages 50 is the same person who departed, in the sense of physical and psychological continuity. But they have become disconnected from the temporal stream that everyone else shares. Their personal history has branched away, flowing at a different rate, rejoining the common stream only upon their return. What does it mean to be the same person across such a journey? If identity depends partly on relationships, on shared experience, on participation in a common time, then relativistic travel challenges identity in ways that no previous human experience has ever approached. The traveler returns to find that their world has moved on without them, that they have been absent, not just in space but in time. They have become, in a sense, a visitor from the past, carrying memories and relationships that now connect to a vanished era. This is not merely a psychological curiosity. It has practical implications for how we might think about relativistic travel as a human endeavor. A person cannot simply leave and return as though no time had passed. They must accept that departure is, in a meaningful sense, a kind of departure from their entire era, a journey not just across space but into the future. The decision to travel at relativistic velocities is a decision to leave everything behind in a way that no previous journey has ever required. And this leads us to something even more surprising about how such journeys would reshape our understanding of the universe itself. At relativistic velocities, the concepts of distance and duration become tangled in ways that challenge our ordinary intuitions. We speak of a star being 10 light-years away, meaning that light takes 10 years to travel from there to here. But this distance is measured in a particular reference frame, the frame of the observer, who sees both the star and themselves as stationary. For a traveler moving at relativistic velocity, the distance is different. Length contraction shrinks the gap, so the traveler measures a shorter distance to the star. Time dilation means the traveler's clocks run slow, so the journey takes less of their time. The star has not moved, the light years have not changed, but the traveler's relationship to the intervening space has transformed. In their frame of reference, the universe has reshaped itself around their motion. This is not an illusion or a trick of measurement. It is a genuine feature of space-time, as real and physical as the time on your watch or the length of your arm. Different observers, moving at different velocities, experience different distances and durations, and all of their measurements are equally valid within their own frames. There is no absolute distance, no absolute time, only the relative measurements made by observers in specific states of motion. What would this mean for navigation and positioning during a relativistic journey? The spacecraft would experience the universe very differently from observers back on Earth. Stars ahead would appear closer together due to aberration, their light blue shifted into unfamiliar wavelengths. Stars behind would appear red-shifted, perhaps invisible. The familiar constellations would distort beyond recognition. Standard navigation techniques, based on the positions and brightnesses of known stars, would need to be extensively modified to account for these relativistic effects. Fortunately, the mathematics of special relativity is well understood. The transformations that describe how positions, velocities, and wavelengths change between reference frames are known precisely and can be calculated with arbitrary accuracy. A sufficiently sophisticated navigation system could correct for aberration and Doppler shifting, reconstructing the true positions of stars from the distorted view the spacecraft perceives. But the computational requirements would be substantial, and the system would need to operate in real time as the spacecraft's velocity changed during acceleration and deceleration phases. There is also the question of relativistic beaming, an effect that concentrates the intensity of light in the direction of motion. At high velocities, light from sources ahead appears not only blue-shifted, but brighter, because the energy of the light is boosted by the Doppler effect. Light from sources behind appears dimmer. This asymmetry would affect how the spacecraft perceives and is perceived by the universe, making forward sensors more sensitive and rearward sensors less effective. And this brings us to another consideration that shapes the experience of relativistic travel: the cosmic microwave background radiation. This faint glow, the afterglow of the Big Bang itself, fills all of space with microwave photons at a temperature of about 2.7 degrees above absolute zero. At ordinary speeds, this radiation is harmless and almost undetectable without sensitive instruments. But at relativistic velocities, the Doppler effect transforms it. For a spacecraft traveling at 90% of light speed, the cosmic microwave background ahead would be blue-shifted into infrared radiation, perhaps even into visible light. The universe ahead would glow with a shifted remnant of the Big Bang itself, a diffuse light from the birth of time. At higher velocities, this radiation would shift further into ultraviolet, then X-ray, then gamma-ray frequencies. What began as a harmless microwave bath would become a source of potentially dangerous high-energy radiation, adding to the challenges of the interstellar medium. The cosmic microwave background behind the spacecraft would be red-shifted in the opposite direction, pushed to longer wavelengths, lower frequencies, lower energy. Eventually, it would shift below the threshold of detectability, vanishing into radio waves too faint and stretched to observe. The universe behind would grow dark and cold, even more so than its already frigid baseline. How close could we truly come to light speed? The answer depends on the energy available, the engineering achievable, and the risks acceptable. There is no sharp boundary, no wall marking the end of the road. You can always get a little closer, add another 9 after the decimal point, approach that asymptote ever more nearly. But each step requires exponentially more effort than the last, and the practical returns diminish even as the theoretical effects grow. At 90% of light speed, time dilation and length contraction become significant factors, transforming interstellar distances from impossibilities into challenges. At 99%, the effects are dramatic, compressing decades of external time into years of personal experience. At 99.9%, the transformation is profound, making journeys across the galaxy survivable in principle within a human lifetime. Beyond that, each additional 9 continues the trend, but at exponentially increasing cost. For practical purposes, the question may not be how close we can theoretically get, but what velocity is worth the effort for a given mission. A journey to a nearby star, 4 light-years distant, requires different capabilities than a journey to the galactic center or another galaxy entirely. The faster you go, the shorter your personal journey time, but also the more energy you need, the more severe the environmental hazards, and the more extreme the temporal disconnect from home. There may be an optimal velocity for different mission profiles, balancing these competing considerations. And this raises a quiet question about the nature of the universe itself. If relativistic travel is possible in principle, if sufficiently advanced civilizations could send travelers across interstellar distances within single lifetimes, why do we see no evidence of such activity? This is a variant of the famous Fermi paradox, the puzzle of why an apparently vast and ancient universe shows no obvious signs of intelligent life beyond Earth. One possible answer is that the challenges of relativistic travel are so severe that no civilization ever overcomes them. The energy requirements, the engineering difficulties, the risks of the interstellar medium. Perhaps these barriers are simply too high for any species, no matter how advanced. Perhaps the dreams of star travel remain dreams forever, even for civilizations far beyond our own. Another possibility is that the universe is larger and older than we appreciate, and that relativistic travelers exist but have simply not reached us yet. Even at velocities close to light speed, crossing galactic distances takes thousands of years from the perspective of the travelers, and even longer from the perspective of stationary observers. The universe may be full of ships making journeys that will not conclude for millennia, their passengers alive and experiencing normal time, their destinations still unimaginably far in their own contracted reference frames. Or perhaps civilizations capable of such travel have found reasons not to make it. Perhaps they have discovered that the costs, energetic, social, existential, outweigh the benefits. Perhaps they have found ways to explore the universe that do not require moving physical beings across vast distances. Perhaps they have turned inward, finding infinite complexity and wonder in their own solar systems, their own planets, their own minds. We cannot know the answer from our present vantage point. We can only note that the physics permits relativistic travel, even as it makes such travel extraordinarily difficult. The universe is open to exploration in principle across its entire vast expanse. Whether anyone will ever actually conduct that exploration is a question that transcends physics, reaching into biology, economics, sociology, and perhaps aspects of existence we have not yet conceived. Let us consider now what would happen in the most extreme cases, where velocities approach light speed so closely that the relativistic effects become overwhelming. At 99.99% of light speed, time dilation reaches a factor of about 70. A single year of ship time corresponds to 70 years elsewhere. A passenger could live through what feels like a normal human lifespan of 80 years, while 5,600 years pass in the rest of the universe. They could depart Earth in the present and return to find themselves in a future more distant than the entire span of recorded human history. At 99.999%, the factor approaches 224. At 99.9999%, 707. At 99.99999%, over 2,000. The numbers scale without limit as you add nines, each one bringing you closer to that unreachable asymptote. In principle, a traveler could skip forward by any amount of time they choose, limited only by how close to light speed they can actually travel. But the experience of such a journey would be strange beyond description. The universe ahead would have collapsed into a brilliant point of almost unimaginable intensity. The combined light of all visible stars, blue shifted and aberrated into a searing disk of high-energy radiation. The universe behind would have vanished into darkness, all light red-shifted below visibility. The traveler would exist in a bubble of normal time, surrounded by a cosmos that is aged by millennia or more in what feels like a moment. What would this mean for a human traveling through space under such conditions? The psychological impact might be as significant as the physical challenges. To watch the universe transform around you, to see cosmic time compression made manifest, to know that everyone and everything you left behind has aged into dust. This is an experience for which nothing in human evolution has prepared us. We are creatures of normal time, beings who expect the world to age alongside us. Relativistic travel would sever that connection fundamentally and irreversibly. And this leads us to one more phenomenon that deserves attention: the relationship between relativistic velocity and gravity. Einstein's general theory of relativity, developed a decade after special relativity, describes gravity not as a force but as a curvature of space-time caused by mass and energy. Objects in free fall follow the natural contours of this curved space-time, paths that appear curved from a distant perspective, but are actually as straight as possible within the warped geometry. Time dilation occurs not only because of velocity, but also because of gravity. A clock in a strong gravitational field ticks more slowly than a clock far from any massive object, and this effect has been confirmed with extraordinary precision using atomic clocks at different altitudes. The relationship between gravitational time dilation and velocity-based time dilation is not coincidental. Both arise from the geometry of space-time, from the way that motion through space and presence near mass affect the passage of time. For a relativistic traveler, these effects would combine in complex ways. During the acceleration phase, if the spacecraft maintains a steady 1g acceleration, the passengers would experience something very much like standing in Earth's gravity. But this is not gravitational time dilation. It is the time dilation of acceleration, which is equivalent in important ways but arises from a different cause. General relativity teaches us that acceleration and gravity are locally indistinguishable, a principle known as the equivalence principle. A person in a closed room cannot tell whether they are standing on a planet or accelerating through space at 1g. The physics is the same. This equivalence has profound implications for understanding the experience of relativistic travel. The passenger in an accelerating spacecraft feels weight, feels time passing normally, feels all the familiar sensations of life on Earth. The strangeness is hidden, revealed only when they compare their clocks with those of distant observers, or when they look outside and see the universe transforming around them. The physics is working constantly, reshaping space-time at every moment, but the passenger floats within their bubble of local normality. And this raises yet another dimension of the journey. What happens to consciousness itself as it travels through space-time at such extreme velocities? We know that consciousness arises from physical processes in the brain: electrochemical signals, neural connections, molecular interactions. These processes occur in time, depend on the sequence of cause and effect, unfold according to the laws of physics. Time dilation affects all physical processes equally, including those that generate consciousness. The traveler does not experience their thoughts slowing down. They experience time passing normally. But their thoughts, their experiences, their very consciousness is stretched out from the perspective of a stationary observer. If you could somehow watch a relativistic traveler from outside, with a magic window into their brain activity, you would see everything happening in slow motion. Their neurons would fire at a fraction of the normal rate. Their thoughts would unfold over extended periods. A sentence spoken in seconds of ship time would take minutes or hours or days from your perspective, depending on the velocity. And yet, The traveler would perceive none of this. To them, their thoughts proceed at the usual pace. Their words take the usual time. Their consciousness flows at its accustomed rate. The slowdown exists only in the comparison, only in the relationship between reference frames. This leads to questions that brush against philosophy as much as physics. What is the rate of consciousness? How fast does subjective experience truly occur? These questions do not have simple answers, and relativistic travel complicates them further. The traveler experiences normal time, but an observer experiences the traveler's time as dilated. Which is real? The answer, according to physics, is both. Neither reference frame has a privileged claim to represent absolute truth. Both are equally valid descriptions of the same physical reality, seen from different perspectives. And this brings us to the deep truth at the heart of relativity, the insight that transformed our understanding of the cosmos in the 20th century. There is no absolute time. There is no absolute space. There is only space-time, a four-dimensional fabric in which different observers slice out different notions of time and space depending on their states of motion. The universe does not have a master clock ticking away in some cosmic control room. It has only local clocks, each keeping perfect time in its own reference frame, each disagreeing with clocks in other frames about how much time has passed. What happens to our sense of the present moment in such a universe? When you think of now, you likely imagine a single instant of time shared by all objects in the universe, a cosmic present that encompasses everything from here to distant galaxies. But special relativity tells us that this intuition is mistaken. The present moment is local, not cosmic. What is now for you may be the past or the future for an observer moving rapidly relative to you. There is no universal now, no shared instant that all observers can agree upon. This has strange implications for the traveler at relativistic velocities. Their now, their present moment, does not correspond to Earth's now. Events that are simultaneous for them are not simultaneous for observers on Earth, and vice versa. The traveler exists in a different slice of space-time, rotated away from Earth's slice by their motion. They share the same universe, the same four-dimensional space-time, but they disagree about how that space-time divides into space and time. How would this feel? The traveler would not notice anything unusual. Their sense of the present moment would seem perfectly normal, perfectly immediate. It is only when they compare notes with Earth, only when they try to synchronize their experiences with those of stationary observers, that the discrepancies emerge. The universe is not a stage on which events unfold in a shared present. It is a complex web of relationships, a fabric in which different threads experience different orderings of events. And this brings us to questions about causality, the relationship between causes and effects that structures our entire understanding of the world. In ordinary experience, causes precede effects. The ball moves after you kick it. The glass breaks after it hits the floor. This ordering seems absolute, inviolable, built into the nature of reality itself. But in a relativistic universe, even this certainty becomes subtle. Special relativity preserves causality within a crucial constraint. Events that are causally connected, where one event can influence another, always maintain their proper ordering across all reference frames. If you send a signal to a distant star, that signal arrives at the star after you sent it, according to all observers, no matter how fast they are moving. The speed of light serves as the ultimate speed limit for information and influence, ensuring that causes always precede their effects. But for events that are not causally connected, events that are too far apart in space for any signal to pass between them, the ordering can differ between reference frames. One observer might see event A happen before event B, while another observer, moving differently, sees event B happen first. Neither is wrong. The events simply have no inherent ordering because they cannot influence each other. For a relativistic traveler, this means that their picture of the universe is subtly different from Earth's picture. Events that appear simultaneous to Earth might appear sequential to the traveler, or vice versa. The history of the cosmos looks different from different perspectives, not because anyone is mistaken, but because history itself is frame-dependent for events that cannot causally influence each other. This does not allow for paradoxes. Causes still precede effects for all events that are causally related. You cannot travel to the past and change history. You cannot receive a message before it was sent. The cosmic speed limit enforces this consistency, ensuring that the universe remains coherent across all reference frames. But the picture that emerges is stranger than our everyday intuitions suggest. A cosmos in which time and causality are woven together in ways that depend on motion and perspective. Let us turn now to what might be called the external view of a relativistic spacecraft, how it would appear to observers who remain at rest while the ship speeds past. We have discussed how the universe appears to the traveler, aberrated, shifted in color, concentrated ahead, and darkened behind. But what would stationary observers see when they look at the ship itself? Here too, the effects of relativity transform perception. A spacecraft moving at relativistic velocity would appear contracted in its direction of motion, squeezed along its length like a compressed accordion. A ship that measures 100 meters long at rest would appear only about 44 meters long to a stationary observer if it were traveling at 90% of light speed. At 99%, it would appear only about 14 meters. At 99.9%, about 4.5 meters. The ship has not changed. Its internal dimensions remain normal for its passengers. But from the outside, it appears flattened. Light from the ship would be Doppler shifted as well. If the ship is approaching, its lights would appear blue shifted to higher frequencies. If it is receding, they would appear red shifted to lower frequencies. The color of the ship itself would change, depending on its direction of motion relative to the observer. A spacecraft painted white might appear bluish when approaching, and reddish when receding. And there is another effect, more subtle but significant. Relativistic aberration changes not only where objects appear to be, but how they appear to be shaped. At high velocities, a spacecraft appears rotated, as though turned at an angle even if it is actually moving straight toward or away from the observer. This is not a real rotation, but an optical effect caused by the finite speed of light in the ship's motion. Light from different parts of the ship arrives at the observer's eye at slightly different times, creating the impression of rotation. These effects would make tracking and identifying a relativistic spacecraft surprisingly difficult. Its appearance would change continuously as its velocity and direction changed. Standard visual identification techniques would fail. Sophisticated sensors and computational systems would be needed to interpret the distorted images and reconstruct the ship's true shape, size, and trajectory. How would such a spacecraft communicate with observers it passes? As we discussed earlier, signals from an approaching spacecraft would be blue-shifted, arriving compressed in time and raised in frequency. Signals from a receding spacecraft would be red-shifted, stretched out, and lowered in frequency. A radio message sent at one frequency would arrive at a very different frequency, requiring receivers that can handle a wide range of wavelengths. A voice message would be pitch-shifted and time-shifted, sounding higher and faster when the ship approaches, lower and slower when it recedes. For a ship traveling at 90% of light speed, the Doppler factor is about 4.5. A radio signal sent at 1 gigahertz would arrive at nearly 5 gigahertz when the ship is approaching, or about 200 megahertz when receding. A voice message would be compressed to about a quarter of its original duration when approaching, stretched to about 4 times its duration when receding. The communication challenge is significant, requiring adaptive systems that can track the ship's velocity and correct for the shifting frequencies in real time. And this brings us back to the fundamental challenge of relativistic travel, the isolation it creates. A ship traveling at high fractions of light speed is cut off from the rest of the universe in multiple ways. Time dilation separates its passengers from the temporal stream of their home. Communication delays make conversation impractical. Visual distortion makes the familiar cosmos unrecognizable. The traveler exists in a bubble of their own reference frame, connected to the larger universe only through the mathematics of Lorentz transformations and the patience of decades-long message exchanges. Would anyone choose such isolation? Perhaps, for certain purposes. Scientific exploration might justify journeys that take the travelers far into the future, allowing them to visit destinations no slow probe could reach in useful time. Survival might drive such journeys. If a civilization faced destruction and sought refuge in the distant star systems. Adventure and curiosity have driven humans to accept terrible risks throughout history. Relativistic travel might simply be the ultimate expression of that drive. But there is something melancholy about the prospect as well. The relativistic traveler sacrifices their connection to their own time, their own people, their own era. They become explorers, not just of space, but of time. Voyagers into a future they cannot share with those they left behind. The journey outward is also a journey forward, and there is no coming back to the moment of departure. And this raises a final set of questions about what we might learn from such journeys. What the universe might reveal to travelers willing to accept the costs. At relativistic velocities, a spacecraft could reach destinations that light itself takes years or decades or centuries to span. What waits at those destinations? What would we find if we could send human observers to distant stars, to the centers of galaxies, to the edges of the visible universe? We know, from telescopes and theory, something about the cosmos at large scales. We know that stars fill galaxies by the hundreds of billions. We know that galaxies cluster into groups and superclusters, stretching across millions of light years. We know that the universe is expanding, carrying those clusters apart at ever-increasing rates. We know that the observable universe extends some 46 billion light years in every direction, a sphere of space within which light has had time to reach us since the Big Bang. Beyond that sphere, the universe continues, perhaps infinitely, but its light has not yet arrived. What would a relativistic traveler actually encounter on a journey through these vast spaces? For most of the voyage, they would encounter nothing but emptiness. The space between stars is staggeringly empty, a vacuum more complete than anything achievable in laboratories on Earth. Scattered atoms of hydrogen, grains of dust, cosmic rays. These would be the only companions for light years at a stretch. The stars themselves would be pinpoints of light, slowly brightening as the destination approached, slowly fading as the origin receded. But the strangeness of the visual experience would provide constant reminder that this is no ordinary journey. The stars would crowd toward the front, aberrated into unfamiliar patterns. Their colors would shift through the spectrum. The cosmic microwave background would glow ahead, blue shifted into visibility, a reminder that the traveler is moving through the afterglow of the Big Bang itself. Behind, darkness would deepen. The trailing universe redshifted into invisibility. As the destination approached, a planet perhaps orbiting a distant star, the spacecraft would need to slow down. Deceleration poses all the same challenges as acceleration. The energy requirements, the time needed, the experience of sustained gravity-like force. The traveler, who spent years accelerating to relativistic velocity, would need to spend comparable time decelerating, watching the universe ahead uncrowd, watching the colors shift back toward normal, watching the destination grow from a point of light into a disk, then a world. What would they find there? We cannot know in advance. Our telescopes can detect planets around distant stars, can measure their sizes and orbits, can even detect hints of their atmospheres. But the details remain hidden by the limitations of distance and resolution. A relativistic traveler could see with their own eyes what we can only infer from light curves and spectra. They could walk on surfaces no human has ever trod, breathe atmospheres no human has ever analyzed firsthand, encounter whatever wonders or dangers await among alien stars. Or they might find nothing. The universe is vast, and most of it appears to be empty. The planets around other stars might be sterile rocks, too hot or too cold or too irradiated for life. The traveler might journey for subjective years to reach a destination that offers nothing but barren landscapes and airless skies. The cosmos does not promise rewards for those who seek it. It offers only the journey itself, the adventure of motion and time, the transformation that comes with approaching the speed of light. And perhaps that is enough. Humans have always journeyed for reasons beyond practical benefit. For curiosity, for challenge, for the simple desire to see what lies beyond the horizon. Relativistic travel would be the ultimate horizon, the boundary beyond which everything we know transforms into something strange and new. The journey would change the travelers, would separate them from their time and place, would offer experiences no human has ever had. Whether that transformation is worth the cost is a question each potential traveler would have to answer for themselves. As we draw toward the end of our exploration, let us consider one more aspect of what it would mean to approach light speed. The philosophical dimension, the shift in perspective that such journeys would require. We have discussed the physics, time dilation, length contraction, Doppler shifts, aberration, energy requirements, radiation hazards. These are the mechanics of relativistic travel, the equations and effects that would govern any such journey. But beyond the mechanics lies a deeper question. What would it mean for human self-understanding? If we became a species capable of traveling at significant fractions of the speed of light, throughout our history, we have expanded our sense of what is possible. We have sailed across oceans that once seemed impassable. We have flown through skies that once seemed beyond reach. We have walked on a world beyond our own, 250,000 miles from Earth. Each expansion has changed us, has shifted our sense of our place in the cosmos, has revealed new horizons that once seemed impossibly distant. Relativistic travel would represent the ultimate expansion. It would make the stars themselves accessible, would open the galaxy to exploration, would extend the range of human experience beyond anything our ancestors could have conceived. But it would also reveal, more starkly than any previous advance, the true nature of the universe we inhabit. A cosmos bound by the geometry of space-time, shaped by the absolute speed limit of light, structured by relationships between motion and time that violate our deepest intuitions. To become a relativistic species would be to confront these truths directly, to live within the equations rather than merely to contemplate them. Time dilation would no longer be a curious prediction. It would be a fact of life, separating travelers from their homes and eras. Length contraction would not be an abstraction. It would be visible in the squashed appearances of the destinations ahead. The speed of light would not be a number in a textbook. It would be the barrier that shapes every journey, the limit that determines what is possible and what is not. Some might find this limiting, a universe constrained by rules that forbid the faster-than-light travel of science fiction. But others might find it liberating, a universe whose rules are known and navigable, whose possibilities, however extreme, are at least defined. We cannot travel faster than light, but we can travel very close to light speed, and in doing so, we can reach any destination the visible universe contains. The journey might take subjective years or decades, but the universe is open. Nothing forbids us from crossing it. And what would we bring back from such journeys? Not just data, not just observations, but experience. The lived knowledge of what it means to exist at the edge of physical possibility. We would know, as no previous generation has known, what time dilation feels like. We would know how the universe looks from the interior of a relativistic reference frame. We would know the isolation and the wonder, the challenge and the revelation. We would know what it means to journey not just across space, but across time, to arrive in a future that no longer remembers our departure. This knowledge would change us. It always has. Every expansion of human capability has brought not just new powers, but new perspectives, new understandings of what we are and what we might become. Relativistic travel would offer the ultimate perspective, a view of the cosmos from motion so extreme that space and time themselves transform. To achieve such travel would be to join a universe that has been waiting for us since the Big Bang. A universe whose deepest secrets lie hidden in the geometry of space-time, in the equations that govern motion at its most extreme. The photon we mentioned at the beginning continues its journey even now, racing through the void at the cosmic speed limit. It has no consciousness, no awareness, no capacity to appreciate the strangeness of its existence. But somewhere in the future, perhaps, human beings might make journeys that approach that photon's experience. They might see the universe transform around them, might watch cosmic time compress and stretch, might live through experiences that challenge everything we think we know about motion and time and existence. The physics permits it. The engineering may someday achieve it. And if it does, the travelers who venture to the edge of light speed will join a select group. Those who have touched the boundaries of what the universe allows, who have felt the equations of relativity in their bones, who have journeyed not just across the stars, but into the deepest truths about the nature of reality. The universe is vast beyond comprehension, ancient beyond reckoning, structured by laws that we have only begun to understand. But within that vastness, within that age, within that structure, there is room for us. There is room for human curiosity, human courage, human wonder. There is room for journeys that span the light years, for experiences that span the centuries, for transformations that span the depths of space-time itself. What happens if humans reach almost the speed of light? Everything changes. Time dilates, space contracts, the cosmos transforms, and we become something we have never been before. A species that has touched the edge of possibility, that has felt the universe bend around its motion, that has journeyed to the frontier where physics itself reshapes experience. That frontier awaits. It has always awaited. And though we cannot yet reach it, though the challenges remain immense and the timescales vast, the laws of physics have left the door open. The speed of light is a limit, but not a wall. We can approach it asymptotically, forever getting closer without ever quite arriving. And in that eternal approach lies the promise of transformation, the promise that one day, somehow, human beings might ride the edge of light itself, watching the universe unfold around them in ways no earthbound observer has ever seen. The equations are patient, the cosmos is vast, and the journey, whenever it begins, will reveal truths we can scarcely imagine. Truths about time and space, about motion and energy, about the nature of existence itself. Those truths await us, hidden in the geometry of space-time, encoded in the mathematics of relativity. And when we finally reach for them, traveling at velocities that transform everything we know, we will discover what it means to live at almost the speed of light. The universe has been keeping these secrets for billions of years, since long before Earth formed or life emerged, or human minds first wondered about the stars. But the secrets are not locked away forever. They are embedded in the structure of reality, waiting for observers curious enough and capable enough to uncover them. Relativistic travel is the key, the experience that unlocks the deepest truths about how space-time behaves when motion approaches its ultimate limit. And so we return, finally, to where we began, to that single photon racing through the cosmos at the speed of light. For the photon, time does not exist. For the photon, the universe is a zero-dimensional point, all destinations equally near, all moments equally present. The photon represents the limit of what motion can achieve, the boundary that nothing with mass can cross. But we can approach that boundary. We can venture close enough to feel time dilate around us, to watch space contract before us, to experience the universe transforming in response to our motion. We cannot become photons. We cannot shed our mass and reach light speed itself. But we can journey into the territory where relativity dominates, where ordinary intuitions fail, where the equations of physics become lived experience rather than abstract theory. That journey lies ahead, perhaps decades away, perhaps centuries, perhaps longer. The challenges are immense, the energy required, the engineering demanded, the hazards confronted, the isolation endured. But none of these challenges represents a fundamental impossibility. They are obstacles, not barriers. They are problems to be solved, not laws to be violated. And when those problems are finally solved, when the first human beings finally accelerate to significant fractions of light speed, they will enter a universe that we can only describe from the outside. They will feel time dilation in the aging of their cells, see length contraction in the approaching stars, experience Doppler shifts in the colors of the cosmos. They will know, in a way that no earthbound theorist can know, what it means to approach the speed of light. That knowledge awaits them. It awaits all of us, as a species, as travelers in a cosmos vast beyond comprehension. The universe invites us to explore it, to push against its limits, to discover its secrets. The invitation has been open since the first human looked up at the stars and wondered what they were. Now, with the mathematics of relativity in our possession, we know something about what the journey would require and what it would reveal. The stars are far away, light years distant, requiring years even at light speed to reach. But those years can be compressed by motion, squeezed down by time dilation into spans that human beings can survive. The journey to Alpha Centauri, 4 light years away, would take 4 years even for a beam of light. But for a traveler, at 99% of light speed, it would feel like less than 7 months. The galaxy itself, 100,000 light years across, would require 100 millennia for light to span. But for a traveler, at extreme relativistic velocity, it could be crossed in a single lifetime. The physics permits it. The universe is accessible, and the transformation that such travel would bring to individuals, to societies, to our entire sense of who and what we are, awaits us on the other side of challenges that are immense but not impossible. We began with a photon, traveling in silence through the void. We end with a question. Will we follow? Will we accept the costs and confront the challenges? Will we journey to the edge of possibility, to the frontier where time and space transform, to the threshold of light speed itself? The universe does not answer. It merely waits, patient and vast, its secrets encoded in the geometry of space-time. The invitation remains open, the equations remain true, and the journey, whenever we choose to begin it, will take us places no human has ever been, places where the very nature of reality bends around our motion, where time flows at unfamiliar rates, where the cosmos reveals itself in ways our ancestors could never have imagined. That is what happens if humans reach almost the speed of light. The universe opens up, time transforms, space contracts, and we become explorers, not just of the cosmos, but of the deepest truths about the nature of existence itself. The journey awaits. It has always awaited. And when we finally embark upon it, we will discover what it means to live at the boundary of possibility, traveling at the edge of light, watching the universe unfold around us in all its strange and beautiful majesty. For now, we remain earthbound, gazing up at stars whose light takes years to reach us. But the mathematics tells us what is possible. The physics shows us the path. And somewhere in the future, near or distant, we cannot know, human beings may finally take that path, finally accelerate toward the cosmic speed limit, finally experience for themselves what it means to approach almost the speed of light. The secrets of relativity await their discovery. The cosmos awaits its explorers. And the journey, whenever it begins, will transform everything we thought we knew about time, space, motion, and existence itself. That transformation is the ultimate answer to our question: what happens if humans reach almost the speed of light? We become something new. We enter a realm where ordinary intuitions fail and extraordinary truths emerge. We touch the boundaries of what the universe allows, and in doing so, we fulfill the deepest promise of human curiosity: to explore, to discover, to understand, to journey into the unknown, and return with knowledge no previous generation has possessed. The photon continues its silent flight through the cosmos, experiencing no time, covering no distance from its own perspective. And perhaps one day, human travelers will follow in its wake, not quite matching its speed, but approaching close enough to feel the universe transform around them. That day may be far away, or it may be closer than we think. The only certainty is that the physics permits it, the cosmos awaits it, and the transformation it would bring exceeds anything we have yet experienced. Almost the speed of light, almost the ultimate limit, almost the boundary where everything changes, almost. But in that almost lies the promise of everything relativity has to offer: the time dilation and length contraction, the visual transformations and communication challenges, the isolation and the wonder, the journey into the future, and the arrival in a cosmos transformed. That is the destination that awaits us. That is what happens when humans approach the speed of light. That is the truth encoded in the equations, waiting to be experienced by those brave enough and capable enough to pursue it. The universe has been keeping this secret for 14 billion years. And one day, perhaps, we will finally learn what it feels like to approach that ultimate boundary, to travel at almost the speed of light, and to discover firsthand what happens when we do. The journey continues. The cosmos waits, and the secrets of relativistic motion remain encoded in the fabric of space-time, ready to reveal themselves to anyone who ventures close enough to light speed to experience them directly. What happens if humans reach almost the speed of light? Everything we think we know transforms. Time becomes flexible. Space becomes malleable. The universe itself becomes a different place, seen from a different perspective, experienced in a different way, and we become travelers in the deepest sense. Voyagers not just across the stars, but across the fundamental structure of reality itself. That voyage awaits. It has always awaited. And when we finally undertake it, we will learn truths about the cosmos that cannot be learned any other way. The speed of light marks the boundary. Almost reaching it transforms everything. And the transformation is waiting for us, patient and eternal, encoded in the geometry of space-time, ready to be discovered whenever we find the means to approach that ultimate limit. The universe is vast. The distances are immense. The challenges are formidable. But the physics permits the journey, and the journey, if we ever make it, will reveal wonders beyond anything we have yet imagined. That is the promise of relativistic travel. That is what awaits at almost the speed of light. That is the transformation that the equations predict, and the cosmos offers to anyone who can achieve the necessary velocity. The photon knows nothing of this. It travels in silence, timeless and instantaneous from its own perspective. But we are not photons. We have mass and consciousness and curiosity. We experience time and wonder about its nature. We see the stars and ask how we might reach them. And the answer, written in the equations of relativity, is both simple and profound. Approach the speed of light, and everything changes. Time dilates, space contracts, the universe transforms, and we become something we have never been before. Beings who have touched the edge of what physics allows, who have experienced reality at its most extreme, who have journeyed to the boundary of possibility and returned with knowledge no earthbound observer can possess. That knowledge is waiting. That transformation is waiting. That journey is waiting. And when we finally undertake it, accelerating toward that cosmic limit, watching the universe reshape itself around our motion, we will discover firsthand what happens when humans reach almost the speed of light. The answer is transformation. The answer is wonder. The answer is a cosmos, revealing its deepest secrets to those who venture close enough to its fundamental limits to experience them directly. That experience awaits. And whatever else the future holds, that possibility remains, encoded in the equations, promised by the physics, waiting for the travelers who will one day approach almost the speed of a light and discover what happens when they do. The journey is long. The challenges are immense. But the destination, that transformation of time and space and perception and experience, is worth whatever effort we must expend to reach it. Almost the speed of light, almost the ultimate boundary, almost the edge of everything physics allows. Almost, and in that almost, all the wonder of relativistic travel awaits its first human explorers. The cosmos is patient. It has waited billions of years already. It can wait a little longer. But one day, perhaps, human beings will finally make that journey. They will accelerate toward the speed of light. They will feel time dilate around them. They will watch space contract before them. They will experience the universe transforming in response to their motion. And they will know, at last, what it means to approach almost the speed of light, what it feels like, what it looks like, what it reveals about the deepest nature of reality. That knowledge is the ultimate reward. That experience is the ultimate destination. And the journey toward it continues even now, as we contemplate the physics that makes it possible and the challenges that must be overcome. The speed of light awaits, just beyond our current reach. And everything we thought we knew about time and space awaits transformation when we finally approach that ultimate limit. Almost the speed of light, almost the boundary of possibility, almost the edge where everything changes. And on the other side of that, almost, revelation, transformation, wonder beyond description. That is what happens if humans reach almost the speed of light. And that is the journey that awaits us, whenever we find the courage and the capability to undertake it. The universe is vast, the secrets are deep, and the transformation is waiting. We have only to reach for it, to accelerate toward that cosmic limit, to discover what lies at almost the speed of light. The equations are ready, the physics is clear, the cosmos is patient. The journey remains to be made, and when it finally is made, everything will change. That is the promise. That is the truth. That is what happens when humans approach almost the speed of light. The transformation awaits. It has always awaited, and it will reveal itself in all its strange and wondrous fullness to whoever finally achieves the velocity necessary to experience it. Almost the speed of light, almost the ultimate boundary, and yet there is more to consider, deeper layers of this cosmic truth that we have not yet explored. For the universe does not simply present us with time dilation and length contraction as isolated phenomena. It weaves them together into a fabric of experience that would reshape every aspect of what it means to be a conscious being moving through space-time. To truly understand what awaits at relativistic velocities, we must follow these threads further into territories where physics and philosophy intertwine in ways that challenge our deepest assumptions about reality. Consider for a moment the nature of memory itself. Our memories are anchored in time, structured by the sequence of events we have experienced. We remember yesterday because it came before today. We anticipate tomorrow because it follows from now. This temporal ordering feels absolute, fundamental to how consciousness organizes itself. But for a relativistic traveler, the relationship between personal time and cosmic time has been severed. Their memories span a personal duration that corresponds to a vastly different duration in the universe at large. What would it feel like to remember a conversation that, from the universe's perspective, happened decades ago? To recall a meal eaten in what feels like last week, but was, by Earth's reckoning, years in the past. The traveler's memories would be accurate. Nothing about their experience would be false or distorted. But those memories would connect to a version of the universe that no longer exists, to moments that have been buried under layers of cosmic time that the traveler never lived through. This temporal displacement creates a kind of solitude that has no earthbound equivalent. Even the most isolated person on Earth shares the same temporal stream as everyone else. Their now is the same now that encompasses all of humanity, all of Earth, all of our local region of space. But the relativistic traveler has stepped outside that shared stream. Their now has diverged, has followed a different path through space-time, has become something personal and separate. And this leads us to something even more surprising about the nature of such journeys. The traveler does not merely experience time differently. They experience causality differently. Events that are simultaneous for them are not simultaneous for observers in other reference frames. The ordering of distant events depends on the state of motion of the observer. This is not a matter of perception or measurement error. It is a fundamental feature of how space-time is structured. What does this mean in practical terms? Imagine a traveler moving at 90% of light speed, passing between two space stations that are stationary relative to each other and separated by a significant distance. For the stationary stations, certain events happen simultaneously. A light turns on at Station A. At exactly the same moment, a bell rings at Station B. But for the moving traveler, these events are not simultaneous. Depending on the direction of travel, either the light comes first or the bell comes first. The traveler's motion has rotated their slice of space-time, changing which events fall within their present moment. This seems almost paradoxical until we remember that simultaneity has no absolute meaning in relativistic physics. There is no cosmic clock that defines which events happen at the same time. There are only local clocks, each keeping perfect time in their own reference frame, each disagreeing with clocks in other frames about the ordering of distant events. The traveler is not wrong when they perceive a different ordering. They are simply inhabiting a different reference frame, slicing space-time along a different angle. But here is the quiet question that this raises. What does this mean for the traveler's relationship with the universe they are moving through. They are not merely passing through space. They are passing through a differently organized version of space-time, one where the present moment encompasses a different set of events than the present moment of stationary observers. They are, in a very real sense, living in a different now than everyone else. This difference becomes more pronounced at higher velocities. At everyday speeds, the rotation of simultaneity is so small as to be undetectable. But at significant fractions of light speed, it becomes substantial. At 99% of light speed, the traveler's present moment is dramatically rotated relative to the present moment of stationary observers. Events that are happening now for people on Earth might be in the traveler's past or future, depending on their location in space. The mathematics handles this consistently. There are no paradoxes, no contradictions. Causality is preserved for all events that can influence each other. But the picture that emerges is one where time is not a universal river flowing at a single rate in a single direction. It is more like a vast landscape that different observers traverse along different paths, each path defining a different notion of now, each observer experiencing a different sequence of cosmic moments. To make sense of this, we must step back for a moment and consider how profoundly this differs from our everyday experience. In ordinary life, we assume that now is universal. When we speak of the present moment, we imagine it extending across the entire universe simultaneously. The sun is shining now. A star is exploding now. A galaxy is spinning now. All of these events share a common moment, a universal present that encompasses everything. But special relativity tells us this intuition is mistaken. The present moment is local, not universal. What is now for you depends on your state of motion. Two observers, moving relative to each other, will disagree about which distant events are happening now. Neither is wrong. Both are correct within their own reference frames. The universe simply does not have a single, universal present moment. For a relativistic traveler, this truth becomes lived experience rather than abstract theory. They exist in a present moment that differs from Earth's present moment, from the present moment of the stars they are approaching, from the present moment of any observer moving differently than they are. They are alone in their now, surrounded by a universe whose temporal structure has been rotated away from their own. And this raises another dimension of the relativistic journey that deserves careful attention: the question of what is real. If different observers disagree about the ordering of events, about what is happening now, about the very structure of time, then what is the true nature of reality? Is there a fact of the matter about which events are simultaneous, hidden beneath the observer-dependent appearances? Or is reality itself observer-dependent, with no absolute truth about temporal ordering? Physicists have debated these questions for over a century, and no consensus has emerged. Some argue that space-time is a four-dimensional block, with all events, past, present, and future, equally real, and the apparent flow of time merely an illusion created by consciousness. Others argue that the present moment is real in a way the past and future are not, even if different observers disagree about which moment is present. Still others argue that the question itself is malformed, that reality does not come in a single flavor, but depends essentially on the perspective from which it is observed. A relativistic traveler would confront these questions directly. They would experience time as flowing normally, would feel the present moment as immediate and real, would remember the past and anticipate the future just as we do. But they would know, because the physics tells them, that their present moment is not shared by observers in other reference frames. They would know that their now is personal, local, defined by their state of motion, rather than by any universal cosmic standard. What would this knowledge do to a person? How would it change their sense of their place in the universe? These are questions we cannot answer from our earthbound perspective. We can only note that relativistic travel would force such questions upon its participants, would make the philosophical puzzles of time and existence into matters of daily experience, rather than abstract speculation. But this raises another quiet question that probes even deeper into the nature of the journey. We have spoken of individual travelers, of single consciousnesses moving through space-time at relativistic velocities. But what about groups? What about communities of travelers sharing a spacecraft, experiencing time dilation together, isolated from the rest of the universe but connected to each other? Here, the picture becomes more complex. Within a single spacecraft, all passengers share the same reference frame. They experience time at the same rate, perceive simultaneity in the same way, share a common now. From their perspective, life aboard the ship proceeds normally. Conversations happen in real time, meals are shared, relationships unfold, all at the ordinary pace of human existence. The strangeness lies entirely in their relationship with the external universe, not in their relationships with each other. This suggests that relativistic travel need not be as isolating as it first appears. A community of travelers sharing a spacecraft would maintain all the normal human connections: friendship, family, collaboration, conflict. They would simply be isolated together, a bubble of shared time moving through a universe that experiences time very differently. But even this companionship has its limits. The community aboard the ship remains cut off from everyone outside it. Messages sent home would take years to arrive, and responses would take years more to return. News of births and deaths, of triumphs and disasters, would arrive in compressed batches, a highlights reel of decades of history, condensed into a few hours of transmission. The travelers would learn of the lives and deaths of friends and family members in reports that span what, to them, feels like a single afternoon. And there is another consideration that shapes the experience of such communities: the journey's end. A spacecraft cannot accelerate forever. Eventually, it must slow down, whether to enter orbit around a destination or to return home. During deceleration, the same forces that compress time during acceleration would operate in reverse. The travelers would feel the same sustained gravity-like force, would watch the universe ahead undistort, would see the Doppler shifts normalize as velocity decreased. But time dilation during deceleration would continue to separate them from the rest of the universe. The journey to a star 10 light-years away might involve years of acceleration, a cruise phase at relativistic velocity, and years of deceleration, all of which contribute to the total time dilation. The travelers would arrive having aged only a fraction of the time that passed elsewhere, regardless of whether they were speeding up, cruising, or slowing down. This leads to a curious thought experiment. Suppose a traveler made multiple journeys, each one taking them to a distant destination and back. Each journey would advance them further into the future relative to their starting point. They would return from each trip to find years or decades had passed, would see the world change around them in jumps rather than in the smooth flow that everyone else experiences. Such a person would become a kind of time traveler, skipping forward through history in discrete leaps. They might visit the same planet across centuries of its development, seeing it transform through colonial settlement, industrialization, and whatever comes after. They would carry memories of eras that no one alive had experienced firsthand, would become a living archive of vanished times. But they would also become increasingly disconnected from the present. Each journey would leave them further out of sync with contemporary society, more alien to the world they returned to. The friends they made between journeys would age and die while they remained young. The knowledge they accumulated would become increasingly outdated with each departure. The traveler would become a visitor everywhere, at home nowhere, a ghost haunting a present that was never quite their own. How would societies cope with such travelers? Would they be celebrated as explorers, honored for their sacrifices? Would they be pitied as exiles, cut off from the normal flow of human life? Would they form communities of their own, bonded by their shared experience of temporal displacement? These questions have no easy answers, but they hint at the social and psychological complexities that relativistic travel would introduce. And this brings us to another consideration that shapes the human dimension of such journeys: the question of purpose. Why would anyone choose to travel at relativistic velocities, knowing the costs involved? What goals could justify the sacrifice of connection, the abandonment of one's own era, the leap into an unknown future? Scientific exploration offers one answer. There are questions about the universe that cannot be answered from Earth, phenomena that can only be observed up close. A relativistic journey to a neutron star, or a black hole, or a distant galaxy would allow observations impossible from any other vantage point. The knowledge gained might transform our understanding of physics, of cosmology, of our place in the universe. For some, this might be worth any personal cost. Survival offers another answer. If Earth faced an existential threat, an asteroid impact, a gamma ray burst, the death of the sun, relativistic travel might offer the only escape. A community fleeing to another star system would sacrifice their connection to the old world, but might preserve the species, might carry human consciousness to new homes among the stars. The alternative might be extinction, making the choice clearer, if no less painful. Curiosity offers a third answer, perhaps the most human of all. Throughout history, people have left behind everything they knew to explore unknown territories. They crossed oceans with no certainty of return, climbed mountains with no guarantee of survival, ventured into wilderness with no promise of reward. Something in human nature drives us toward the unknown, toward the edge of the possible, toward experiences that challenge and transform us. Relativistic travel would be the ultimate expression of this drive, the journey beyond all previous journeys. But whatever the purpose, the experience would transform the travelers in ways they cannot fully anticipate. They would leave as citizens of one era and return as visitors to another. They would carry knowledge and memories that connect to no living experience. They would become bridges between times, human threads linking past to future across gaps that no one else could span. And here is where things become stranger still. We have spoken of travelers moving at constant relativistic velocities, but acceleration opens additional dimensions of experience. During sustained acceleration, passengers feel a force indistinguishable from gravity. A spacecraft accelerating at 1 g would feel exactly like a room on Earth's surface. Passengers could walk, sit, pour drinks, drop objects, all behaving exactly as they would under normal gravity. This is not a coincidence. Einstein's principle of equivalence states that gravitational acceleration and inertial acceleration are locally indistinguishable. A person in a closed room cannot tell whether they are standing on a planet or accelerating through space. The physics is identical. This equivalence is not merely a curiosity. It is the foundation of general relativity, the theory that describes gravity as a curvature of spacetime. For a relativistic traveler undergoing sustained acceleration, this equivalence would be lived reality. They would experience what feels like normal gravity throughout the acceleration phase, which might last years of ship time. They could live relatively normal lives during this phase, sleeping in beds, eating at tables, exercising in gyms, all while hurtling through space at ever-increasing velocity. But the equivalence principle has implications beyond comfort. It connects acceleration to gravity, and gravity to the curvature of spacetime. A spacecraft undergoing sustained acceleration is creating, in effect, its own local gravitational field. The passengers experience this field as normal gravity, but it is actually the result of their acceleration through flat spacetime. The mathematics of general relativity describes both situations identically. This leads to subtle effects that would shape the traveler's experience. Time passes slightly faster at higher altitudes in a gravitational field. This is gravitational time dilation, confirmed by experiments with atomic clocks at different heights. In an accelerating spacecraft, the equivalent effect means that time passes slightly faster at the front of the ship than at the back. The difference is extremely small for realistic spacecraft, but it is real and measurable in principle. What would this mean for passengers? In practical terms, almost nothing. The effect is far too small to notice over human lifetimes, but it illustrates how deeply space-time is affected by acceleration and motion, how the fabric of reality bends and warps in response to physical conditions. The relativistic traveler is not merely moving through space-time. They are reshaping it around them, creating local distortions that affect the flow of time itself. And this brings us to a phenomenon that deserves careful attention: gravitational waves. General relativity predicts that massive objects undergoing acceleration produce ripples in space-time that propagate outward at the speed of light. These gravitational waves have been detected by sensitive instruments on Earth, confirming one of general relativity's most dramatic predictions. A relativistic spacecraft undergoing acceleration would also produce gravitational waves, though extremely weak ones. The spacecraft's mass is tiny compared to the astronomical objects that produce detectable gravitational waves, colliding black holes, merging neutron stars. So its gravitational radiation would be essentially unmeasurable. But the principle remains. The spacecraft is not merely moving through space-time, it is disturbing it, sending ripples out into the cosmos that carry information about its motion. This connects the traveler to the universe in a subtle way. Even in the depths of interstellar space, far from any star or planet, the spacecraft's presence makes itself known through its gravitational influence. Space-time itself registers the traveler's passage, recording their acceleration in waves that spread outward at the cosmic speed limit. The traveler is never truly alone. They are always in conversation with the fabric of reality itself. But this raises another quiet question about the nature of such journeys. We have focused on the physical effects of relativistic travel, the transformations of time and space and perception. But what about the practical challenges? What would travelers actually need to survive journeys lasting years or decades of ship time? The most fundamental need is life support. Humans require oxygen, water, food, and shelter from the void. For short missions, these can be carried aboard. But for journeys spanning years, the supplies required would be enormous. Hundreds of kilograms of food per person per year, thousands of liters of water, continuous oxygen generation, and carbon dioxide removal. Carrying all of this would add tremendous mass to the spacecraft, mass that must be accelerated to relativistic velocities. The solution, most likely, would involve closed-loop life support systems, recycling water, regenerating oxygen, growing food aboard the ship. Such systems have been studied extensively for long-duration space missions, though none have been tested at the scale required for interstellar travel. The challenges are substantial: maintaining soil fertility over decades, preventing the accumulation of toxins, ensuring genetic diversity in crops, managing the psychological needs of passengers confined to a closed environment for years on end. And psychological needs deserve particular attention. Humans are social creatures, evolved for life in communities, in environments that change and grow around them. A spacecraft, however large, would be a static environment. The same walls and corridors year after year, the same artificial lighting, the same recycled air. The destination would be visible, a star growing slowly brighter over years, but unreachable in any meaningful sense during the journey itself. How would travelers maintain their mental health under such conditions? Studies of isolated communities on Earth, Antarctic research stations, submarine crews, space station astronauts offer some guidance. Meaningful work helps. Varied activities help. Strong social bonds help. But even the longest Antarctic winter lasts only months, not years or decades. The psychological challenges of interstellar travel would exceed anything humans have experienced. Some have proposed technological solutions, virtual reality environments that offer simulated variety, hibernation systems that allow passengers to sleep through the journey, artificial companions that provide social interaction. Each of these raises its own challenges and ethical questions. What does it mean to spend years in virtual reality? Who remains awake to maintain the ship while others sleep? Can artificial relationships substitute for human connection? These questions have no easy answers, but they highlight the human dimension of relativistic travel. The physics may permit such journeys, but humans must survive them, must emerge at the destination physically and mentally intact, must be capable of whatever tasks await them upon arrival. The engineering of relativistic travel must encompass not just propulsion and shielding, but the full complexity of human needs. And this leads us to consider what might await at the journey's end. We have spoken of the journey itself, of the transformations experienced along the way. But ultimately, the purpose of travel is arrival. What would travelers find when they finally reached a distant star system? Our telescopes have revealed thousands of planets orbiting other stars, We know that planets are common in the galaxy, that many stars host multiple worlds of various sizes and compositions. Some of these planets orbit in their stars' habitable zones, the regions where liquid water might exist on a planet's surface. Whether any of them actually harbor water, or life, or conditions suitable for human settlement remains unknown. A relativistic traveler would have the opportunity to answer these questions directly. They could enter orbit around an exoplanet, study its atmosphere and surface, land and walk upon its ground. They could determine whether life exists there, whether humans could survive there, whether a new civilization might take root on alien soil. This knowledge could not be gained any other way. No telescope can match the resolution of direct observation. No probe can replace the judgment of human observers. But arrival would also bring challenges. After years of travel, the spacecraft systems would be aged, its supplies depleted, its passengers weary. They would need to establish operations in an unfamiliar environment to survive on whatever resources the destination offers, to build a new life light years from any possible help. The isolation that characterized the journey would continue at the destination, where any message home would take years to arrive and years more for a response. What kind of people would undertake such a journey? What kind of communities would form at the destination? These questions touch on sociology, psychology, perhaps even the future evolution of human nature itself. The travelers would be different from those who stayed behind, selected by their willingness to sacrifice, shaped by their experiences during the journey, adapted to conditions that no earthbound human has faced. And here is where things become stranger still. We have assumed throughout this discussion that the travelers would be biological humans, flesh and blood, subject to all the limitations and needs of organic life. But what if they were not? What if the travelers were something else entirely? Advances in artificial intelligence and computer technology suggest that, at some point in the future, it might be possible to create minds that exist entirely in silicon or some other substrate. These artificial minds might be copied, backed up, transmitted as information. They would not need food or oxygen or water. They would not age in the biological sense. They might be paused indefinitely and restarted without harm. For such minds, relativistic travel would present very different challenges and opportunities. They could be stored in compact, resilient forms, requiring minimal life support. They could experience the journey in any way they chose, living through it in real time, pausing for long periods, accelerating their processing to make the journey seem shorter. They could be transmitted to the destination ahead of any physical spacecraft, arriving as information to be loaded into awaiting hardware. The philosophical questions raised by such entities are profound. Would they be conscious in the way biological humans are conscious? Would they have experiences, feelings, a sense of self? Would a mind copied multiple times be one person or many? These questions remain unanswered, but they hover at the edge of any discussion of future interstellar travel. Whether biological or artificial, conscious travelers to distant stars would face a common challenge: the vastness of the universe and the puniness of any single journey within it. Even at 99.9% of light speed, the Milky Way galaxy would take tens of thousands of years to cross from Earth's perspective. The nearest large galaxy, Andromeda, lies over 2 million light-years away, a journey that would take millions of years, even at relativistic velocities. The observable universe extends billions of light years in every direction, distances so vast that no journey, however fast, could span them in any reasonable time. The speed of light is a generous limit in some ways. It permits travel to nearby stars within human lifetimes, at least from the traveler's perspective. But it is also a confining limit, boxing us into a tiny corner of the cosmos, making most of the universe forever inaccessible. The relativistic traveler can venture far by earthbound standards, but by cosmic standards, they remain confined to a small neighborhood, a single arm of a single galaxy, in a universe containing hundreds of billions of galaxies. And the universe is expanding. The most distant galaxies are receding from us at speeds that approach and even exceed the speed of light. Not because they are moving through space faster than light, but because space itself is expanding, carrying them away. These galaxies lie beyond our cosmic horizon, forever unreachable regardless of how fast we might travel. The observable universe, already incomprehensibly vast, represents only a fraction of the whole, and that whole is receding ever further from our grasp. What does this mean for the relativistic traveler? It means that their journeys, however ambitious, remain confined to a finite, shrinking region of the cosmos. They can explore nearby stars, perhaps nearby galaxies, given enough time and ambition. But the vast majority of the universe lies beyond any possible reach, separated from us not by mere distance, but by the expansion of space itself. This might seem discouraging, a cosmic barrier that mocks our aspirations. But perhaps it is simply realistic, a reminder of our scale in the cosmos. We are small beings, on a small planet orbiting a modest star. The universe is not made to our measure. It exceeds our capacities in every direction, as it must for any finite beings within an infinite or nearly infinite cosmos. And yet, we can reach the stars. We can, in principle, travel to distant suns, walk on alien worlds, see with our own eyes what no earthbound telescope can reveal. The speed of light limits us, but does not stop us. The universe is accessible, at least in part, to anyone who can achieve the necessary velocity. This is the promise of relativistic travel, not the conquest of the entire cosmos, but the exploration of our neighborhood within it. Not the transcendence of all limits, but the navigation of the limits we face. Not godlike power, but human persistence in the face of cosmic vastness. The journey awaits. The physics permits it. The engineering, however challenging, does not violate any fundamental law. And the transformation that such travel would bring to individuals, to societies, to our understanding of ourselves and our place in the universe, remains there to be discovered by whoever finally achieves it. Almost the speed of light, almost the ultimate boundary, almost the threshold where everything we know transforms into something new. The transformation is patient. It has waited since the Big Bang, since the first moment when light began to travel through the newborn cosmos. It will wait as long as necessary, encoded in the equations of relativity, implicit in the geometry of space-time. And when we finally reach for it, when we finally accelerate toward that cosmic limit, we will discover what has been waiting for us all along, a universe stranger and more beautiful than we ever imagined, seen from a perspective no earthbound observer can share. That is the reward for approaching almost the speed of light. That is what the cosmos offers to those who venture toward its ultimate boundary. The journey is long. The challenges are immense. But the destination, that transformation of time and space and experience itself, is worth every effort we might expend to reach it. Almost the speed of light, almost the ultimate limit. Almost, and in that almost, everything the universe has to teach us about the nature of reality itself. The stars are waiting. They have always been waiting. And one day, perhaps, human beings will finally answer their silent invitation, will finally accelerate toward the cosmic speed limit, will finally experience what it means to approach almost the speed of light. That day may be distant, or it may be closer than we think. The only certainty is that the physics permits the journey. The cosmos invites the exploration, and the transformation awaits its first human witnesses. We are small, and the universe is vast. But we are also curious, and the universe is accessible. The speed of light limits us, but does not stop us. The distances daunt us, but do not defeat us. The challenges await solutions, the journeys await travelers, the destinations await explorers. Almost the speed of light, the boundary where everything changes, the threshold beyond which we become something we have never been before. That threshold awaits, and when we finally cross it, when we finally approach, that transforms everything, we will discover what the cosmos has been keeping secret since the beginning of time. The journey continues, the stars beckon, and the transformation waits, patient and eternal, for whoever finally achieves the velocity necessary to experience it. And yet, there remains one more dimension of this cosmic story that deserves our attention. We have explored the physics, the engineering, the psychology, the philosophy, but we have not fully considered how relativistic travel might reshape human civilization itself, how it might transform our species from inhabitants of a single world into something far more expansive. Consider what happens when the first successful relativistic journey is completed. Travelers depart Earth, accelerate to near-light velocities, cross the void to another star system, and arrive safely. They send word home, a signal that takes years to traverse the distance, but eventually reaches Earth with confirmation of success. What happens next? The news would transform human consciousness. For all of history, Earth has been our only home, our only point of reference, the totality of our existence. Suddenly, it would become one of two places where humans live. The psychological impact would be immense, comparable perhaps to the first photographs of Earth from space, but far more profound. We would know, not merely intellectually, but practically, that our species is no longer confined to a single world. And once the first journey succeeds, others would follow. The technology that enabled one journey would enable many. Different groups might depart for different destinations, each following their own vision of what life among the stars might be. Over generations, human settlements might spread across nearby star systems, each one a new outpost of terrestrial life, each one developing in its own direction. But here is where time dilation creates something unprecedented in human history. These settlements would not remain synchronized. A community departing for a star 10 light years away would experience only a few years of travel, but Earth would age decades during their journey. By the time they arrive and establish themselves, Earth has moved on. By the time news of their success reaches Earth, more decades have passed, and any subsequent contact between Earth and the colony would be delayed by years in each direction. The result would be a fragmentation of human time. Different settlements would exist in different temporal streams, each moving forward at its own pace relative to the others. A person born on Earth and a person born in a colony might be contemporaries in some absolute sense, but they would never experience the same present moment. Their cultures would evolve independently. Their languages would drift apart. Their histories would diverge. This is unlike any previous human diaspora. When populations spread across Earth, they remained in roughly the same temporal stream. Messages could be exchanged within months, if not days or hours. Cultures could influence each other. Ideas could spread. A sense of shared humanity could be maintained. But between star systems, separated by light years, these connections would be stretched to the breaking point. What would happen to human identity under such conditions? Would we remain a single species, a single civilization, or would we fragment into separate lineages, each evolving in its own direction? The physical differences might be small at first. Humans are humans wherever they live. But the cultural differences would compound over generations. Different environments would favor different adaptations. Different challenges would produce different technologies. Different isolation would produce different histories. And this raises another quiet question about the long-term fate of interstellar humanity. If human settlements spread across many star systems, and if those settlements evolve independently, what is the ultimate trajectory? Might humanity split into multiple species, each adapted to its local environment? Might civilizations rise and fall independently, with no communication between them? Might the human diaspora become, over millions of years, as diverse and unconnected as the species in Earth's fossil record? These questions have no certain answers. They depend on factors we cannot predict. The technologies that will be developed, the environments that will be encountered, the choices that will be made by generations not yet born. But they highlight the stakes of relativistic travel. It is not merely a way to visit distant places. It is a way to reshape the human future, to create possibilities that do not currently exist, to transform our species in ways we can barely imagine. And here is where the physics of relativity creates something even stranger. We have noted that different star systems would be separated not just by space but by time. But for travelers moving between systems, the relationship with time becomes even more complex. A person who makes multiple interstellar journeys might age more slowly than anyone who stays in one place. They might become a temporal anomaly, a living connection between eras that no one else spans. Imagine a traveler who departs Earth in the year 2200, makes a journey to a nearby star and back, and returns in the year 2250, having aged only 5 years. They depart again, make another journey, and return in 2300, having aged another 5 years. After several such journeys, they have aged only decades, while centuries have passed on Earth. They carry memories of the 2200s into the 2400s. They have witnessed the transformation of human civilization, not through the slow accumulation of years, but through discrete jumps, each one revealing a changed world. Such a person would become something unprecedented, a witness to historical time, a consciousness that spans eras, normally separated by death. They would remember things that everyone else knows only from books. They would have shaken hands with people who have been dead for centuries. They would embody continuity, a across gaps that no other human can bridge. What would such experience do to a person? How would it change their sense of identity, of belonging, of purpose? These questions touch on the deepest aspects of what it means to be human, aspects that have never been tested in the way relativistic travel would test them. And there is yet another phenomenon that shapes this picture: the possibility of relativistic civilizations, societies built around travel at near light speeds. Such civilizations would have very different relationships with time and space than any society we know. They might think in terms of proper time, the time experienced by travelers, rather than coordinate time, the time measured by stationary observers. They might consider journeys of decades to be normal, acceptable, routine parts of life. They might develop cultures adapted to the temporal fragmentation that relativistic travel creates. What would such cultures be like? Would they value mobility over rootedness, journey over destination? Would they develop rituals for departure and arrival, for the reunions that span generations, for the farewells that become permanent? Would they evolve new concepts of family, of community, of belonging, adapted to the reality of time dilation? These questions exceed our current imagination, but they hint at the cultural transformations that relativistic travel might bring. And this brings us to consider the very long term, the fate of interstellar humanity over millions or billions of years. If humanity survives and spreads among the stars, we would become something far vaster than we are today. Billions of worlds might eventually host human populations, each one a variation on the original theme, each one contributing to a diaspora spanning the galaxy. But even a galaxy is finite. The Milky Way contains perhaps 400 billion stars, spread across a disk 100,000 light-years in diameter. At relativistic velocities, the galaxy could be crossed in perhaps 100,000 years from Earth's perspective, though far less from the traveler's perspective. Over millions of years, human settlements might spread to every corner of our galaxy, might fill every suitable world with variations on terrestrial life. And then what? The nearest major galaxy, Andromeda, lies over 2 million light-years away. A journey there would take millions of years from the perspective of those who stay behind, though much less for the travelers themselves. The gap is immense, but not infinite. In principle, humans might eventually spread beyond our galaxy, might begin the colonization of the local group, might extend our reach across millions of light-years. But the universe is expanding. The most distant galaxies are receding at speeds that effectively place them beyond any possible reach. The observable universe, vast as it is, represents only a shrinking fraction of the whole. Over billions of years, the cosmic horizon will contract, hiding ever more of existence behind an impenetrable veil. Even a civilization that spreads across its home galaxy will eventually find itself isolated, cut off from ever more distant regions by the expansion of space itself. This is the long-term fate that physics predicts. Not a universe gradually unified by expanding civilizations, but a universe gradually fragmenting into isolated islands, each one containing whatever intelligence happens to exist there, each one forever separated from the others by the expansion of space. For a relativistic traveler contemplating this fate, the message is mixed. On one hand, the speed of light permits exploration and settlement across vast distances, at least by cosmic neighborhood standards. On the other hand, The expansion of the universe imposes ultimate limits that no technology can overcome. We can spread among the stars, but we cannot spread everywhere. We can explore our cosmic neighborhood, but we cannot explore the entire cosmos. Perhaps this is fitting. We are finite beings, and we should expect to occupy only a finite portion of existence. The universe exceeds our grasp, as it must for any beings that exist within it rather than encompassing it. The speed of light gives us a generous domain to explore. Billions of stars, countless worlds, mysteries enough for millions of years of investigation. That it also imposes limits should not surprise us. Everything has limits. Even the universe itself may be finite, bounded by edges we cannot perceive, or by a geometry that wraps back on itself. And this brings us back, finally, to where we began. Somewhere in the observable universe, a photon is traveling at the speed of light, experiencing no time, covering no distance from its own perspective. And someday, perhaps, human travelers will follow in its wake, approaching that cosmic velocity as closely as physics permits, experiencing the transformation of time and space that only relativistic motion can provide. They will leave behind everything they know, not just physically, but temporally. They will enter a different stream of cosmic time, will experience a different sequence of universal moments. They will see the universe transformed around them, will feel the equations of relativity in their bones, will know firsthand what it means to approach almost the speed of light. And when they arrive at their destinations, distant stars, alien worlds, places no human has ever seen, they will carry with them the accumulated wisdom of a species that began its existence on a single planet and gradually extended its reach across the cosmos. They will represent not just themselves, but all of humanity, all of Earth, all the generations that came before and made their journey possible. This is the promise of relativistic travel. This is what awaits at almost the speed of light. This is the transformation that the equations predict, and the cosmos offers to anyone who can achieve the necessary velocity. The journey is long. The challenges are immense. But the destination, that transformation of time and space and human possibility, is worth every effort we might expend to reach it. Almost the speed of light, almost the ultimate boundary, almost the threshold where everything changes. And on the other side of that almost, a universe waiting to be explored, secrets waiting to be uncovered, transformations waiting to be experienced by whoever finally ventures close enough to light speed to discover them. The photon continues its journey, timeless and instantaneous from its own perspective, and somewhere in the future, human beings may finally join it, traveling at the edge of possibility, watching the cosmos transform around them, discovering what it means to exist at almost the speed of light. That discovery awaits. It has always awaited, and it will reveal itself in all its strange and wondrous fullness to whoever finally makes the journey. The stars are patient, the physics is eternal, and the transformation remains there, encoded in the equations of relativity, waiting for its first human witnesses. Almost the speed of light, almost the ultimate limit, almost everything, and in that almost, a universe of wonder waiting to be found. But let us not end without considering one more facet of this remarkable story, a dimension that connects the physics of relativity to something deeply human, the question of legacy. When we think about journeys to distant stars, we often focus on the travelers themselves, on what they will experience and discover. But what about those who make such journeys possible? What about the generations who build the technologies, who solve the problems, who lay the foundations for voyages they themselves will never make? The history of human exploration is filled with such figures. People who contributed to great journeys without participating in them. The shipwrights who built the vessels of discovery. The cartographers who mapped the routes. The scientists who developed the instruments. The countless workers who supplied the expeditions. Their names are largely forgotten, but their contributions were essential. Without them, the famous voyages would never have happened. Relativistic travel would require similar contributions on a scale humanity has never before attempted. The technologies needed, the propulsion systems, the shielding, the life support, the navigation, would demand the efforts of generations. The people who developed these technologies might live and die without ever seeing them used. They would be working for a future they can imagine but cannot share. What motivates such contributions? Why would anyone dedicate their lives to projects they will never see completed? The answers touch on the deepest aspects of human nature. Our capacity for hope, our ability to care about generations not yet born, our willingness to be part of something larger than ourselves. These are the qualities that have driven every great human achievement, every cathedral built over centuries, every institution designed to outlast its founders. Relativistic travel would call upon these qualities as never before. The timescales involved, decades to build the technologies, more decades for the journeys themselves, exceed individual human lifetimes. The projects would require not just technical brilliance, but a kind of civilizational patience, a willingness to sustain effort across generations toward goals that will benefit people not yet conceived. And this connects to something profound about the human relationship with time. We are mortal beings, confined to brief spans of existence in a cosmos that measures time in billions of years. We cannot personally witness the long arcs of history, cannot see where our efforts lead, cannot know whether our contributions will be remembered or forgotten. And yet, we act anyway. We plant trees whose shade we will never enjoy. We build institutions that will outlast us. We work for futures we will never see. Relativistic travel would be the ultimate expression of this human capacity. The travelers who finally reach distant stars will be the beneficiaries of countless previous generations, of scientists and engineers and workers who contributed to the effort without sharing in the reward. Those travelers will carry with them not just their own lives, but the accumulated hopes and labors of everyone who came before. And what they find at their destinations, whether barren rocks or living worlds, whether emptiness or wonder, will be the answer to questions that humanity has asked since we first looked up at the night sky. Are we alone in the universe? Is there a place for us among the stars? What lies beyond the next horizon and the horizon after that? These questions have no guaranteed answers. The universe does not owe us discoveries, does not promise that our explorations will be rewarded. The travelers who reach distant stars may find nothing but silence, may confirm that Earth is the only home we will ever have, may return with knowledge that humbles rather than exalts. But even such knowledge would be valuable, would be the truth about our place in the cosmos, would be what we set out to find. And if they find more, if they discover life, or habitable worlds, or mysteries beyond our current imagination, then the journey will have been worth every sacrifice, every effort, every generation that contributed to making it possible. The universe will have revealed itself as richer than we knew, as containing possibilities we had only dreamed of, as offering a future for humanity beyond anything our ancestors could have conceived. This is why the question of relativistic travel matters. It is not merely a technical puzzle, not merely an engineering challenge. It is a question about who we are and who we might become, about what we value and what we are willing to sacrifice, about our relationship with time and with the generations that will follow us. The physics permits the journey. The cosmos offers the destination. And the choice whether to pursue these possibilities or to remain confined to our single world belongs to us, to our species, to the decisions we make about what kind of future we want to create. Almost the speed of light, almost the ultimate boundary, almost the threshold where everything we know transforms into something new. The transformation awaits, patient and eternal. It has waited since the beginning of time. It will wait as long as necessary. And when we finally reach for it, when we finally accept the invitation that the cosmos has always extended, we will discover what has been waiting for us all along, hidden in the equations of relativity, encoded in the geometry of space-time, ready to reveal itself to whoever finally approaches almost the speed of light. The stars are calling, the journey awaits, and the universe, in all its strange and wondrous vastness, remains there to be explored by whoever finally answers that call. That is the promise. That is the truth. That is what awaits at almost the speed of light.